Hi, everybody. We are going to start our last chapter of the year. This is very exciting. Um, so, our last chapter will be on vectors. And vectors, if you look at this vector, it looks a lot like a ray that we studied in geometry. Okay. A vector will have both magnitude and direction. Okay. And I'll get into that in a second. Notice the different ways we can label the vector. Okay, so it starts at O and it goes to P. And we can also label it with a lowercase printed a, but we also have to put that vector symbol above it. Okay, so an example of a vector with a 3-inch magnitude and the direction or amplitude of 30 degrees, what we have to do is we have to remember that, of course, this is our 0-degree mark. Okay, so we have a 30-degree direction if we go 30 degrees of, rotating from the 0-degree mark from the x-axis. And we were told it's a 3-inch vector, so I estimated that to be 3 inches. Vectors can be equal, but they have to have the same magnitude and same amplitude. So if you notice, A and C are facing in the same direction and they are the same length. So they are the same, or they're equal. Opposite vectors, they're the same length, but they're going in the exact opposite direction. So 180-degree difference there. Okay, so here's where we're going to really get started with vectors. So what we're going to be talking about is finding the resultant of vectors. Now, I have a clip here of Ellen's Game of Games when two people are trying to get the apple. One's getting a red apple, one's getting a green apple, and they're pulling each other in different directions. And where do they actually wind up going? Well, where they wind up going is the resultant of the vector. And we have two methods for calculating the resultant of a vector. Okay. Another example is if you were swimming in the ocean and the waves were pushing you. You might be swimming a certain direction at a certain speed. The waves are going in a certain direction at a certain speed, and you wind up getting pushed in a certain direction, okay, with a certain speed. So that's just another example. So, two ways that we can do this. The first way is called the parallelogram method. That's going to look like this. So suppose you have a vector going this way, okay, at, we'll say it's 12 centimeters long, so that's the magnitude. And we have another vector going this way, or pulling that direction, or pushing that direction, okay, and that vector is represented by 3 centimeters. For the parallelogram method, what we can do is we sort of complete this parallelogram. So we copy the bottom up here, and we copy the left at the end here. And what we find out is that the resultant is right there. So in other words, if two forces were pushing or pulling on an object, one going this way in a stronger manner than the one going this way, it would actually wind up going in that direction. Okay. The method that I prefer to use is actually the triangle method, which is also called tip to tail. So we again have that 12 centimeter going in this direction, so it's like 0 degrees. And instead of drawing out the whole parallelogram, I just put where the first one ends, the second vector this way. Okay? And what that does for us is it allows us to see that the resultant will be here. And we'll have ways to figure out how long that is and what direction. Okay, that's really what we're going to be concerned with the resultant. So here I have my first example. And it says Marvin is rowing a boat across the river. Okay, so imagine he's rowing the boat across the river. He was rowing at a rate of 2 miles an hour. The current was flowing at a speed of 4 miles an hour. Okay, so we have the current going 4 miles an hour this way. Okay, and we have Marvin who's trying to go across the river at 2 miles per hour this way. And what's actually going to happen is Marvin's going to be floating like this. Okay, we can figure out two things about this. We can figure out the magnitude and we can figure out the direction. Okay, first of all, for magnitude, what's nice is this is a right angle. So we can use our Pythagorean theorem. Okay, so 4 squared plus 2 squared equals c squared. Okay, this is our c value right here. 16, 4, that's 20, equals c squared. And of course, we can take the square root of each side. And I do believe we get 4.5, 4.4 something. Okay, so that's really the magnitude that Marvin will travel. Okay. Second thing we can do here is we can find out the angle that Marvin's going to travel at. So what we can do is, because we have opposite and adjacent, we can take the tangent of theta, which equals 2 over 4. And after this problem, we're not going to even write this part out because we're just going to do inverse tan, inverse tan. So we can say that theta equals the inverse tan of the opposite over adjacent. And if you go ahead and put that in your calculator, you'll get the angle for Marvin's travels. And that should come out to be about 26.6 degrees. So what that means is Marvin is not able to just travel straight across the river. Because he's being pushed this way, he's actually going at a 26.6 degree angle, and he'll travel a total distance of about 4.5 miles. Okay, so we can break a vector into two components, the horizontal component and the vertical component. In other words, when we look at this vector right here, which is 10 inches long, how far from the initial point to directly below the end of the vector, how long is this? And then, whoops, and how high up is this distance right here from where it starts at the bottom and increases? Okay, so what we have here is, guess what, another right triangle. Okay, and this one, just because it happens to have that 30 degrees, happens to be a special right triangle. So you don't even need to do anything. You should know 10 divided by 2 is 5, and this side over here is 5 times the square root of 3. Okay, that doesn't always happen. It's just because this is a special right triangle. Okay, and what we can do here is, in order to find the x component, what we can do is take the magnitude, or the length of our vector, and multiply it by the cosine of the amplitude. In other words, the direction. Okay, and the way we can write that is magnitude of the vector, I'm calling it vector v, times the cosine of our angle. Okay. For the y component, or the height, and again, this is going to be really important when we don't have a special right triangle. What we'll do is we'll take the magnitude of the vector times, guess what, the sine of the amplitude. So the sine of our angle. Okay, and so that's going to look like this. The magnitude of the vector times the sine of the angle. All right, so what does that mean for this problem? And again, we'll pretend, we didn't know that these values are 5 and 5 root 3. We could have calculated them with the little formula that we got. So 10, because that's the magnitude of the vector, times the cosine of 30. Well, you can put that in your calculator, or you can just know your values. And if we put this in our calculator, we would get approximately 8.66. And just in case you didn't know, 5 root 3 is 8.66. Okay, for the y component, we could have done 10 times the sine of 30. Okay, we know sine of 30 is 1/2, so we don't even have to put this in our calculator. 10 times 1/2 is 5, and that is what we got here. Okay, but again, we kind of knew that because of special right triangle. This is going to be very important when our triangles are not special. So you might want to put a big star around that. Okay, so we can represent vectors algebraically. And this is very, very important because it's very efficient. So when we're looking at vectors, we're looking at the initial point and the terminal point. And what we can do is we can represent from the beginning to the end of our vector using this little formula right here. And you might say, well, that looks familiar. That looks a lot like the distance formula, which, by the way, is a derivative of the Pythagorean theorem. And I would tell you, you're absolutely right. What you need to know here is that the x sub 2 and the y sub 2 will be where the vector is going to. In other words, that's where the arrow is. And the x sub 1 and the y sub 1 are where the vector starts, or it's coming from. Okay, so vectors have directions. So that's going to be really important. So the best way, I think, to actually make sense of this is to do an example. Oh, by the way, I didn't point this out. Component form will use these little pointy points. Okay, so let's do this little example here. So it says, write the ordered pair in component form that represents the vector from 7, -3 to -2, -1. So the first thing we're going to do is we're going to sketch a little diagram. So here's our diagram. We're going to plot these points. 7, -3. Oops, should move that over. Okay. So we'll have the point 7, -3. And the other point that we were given was -2, -1. Okay, so it says from here to this. So I'm going to put that little arrow there. And what I'd like to do is I'd like to make a little right triangle out of this. Okay, because what we're going to try to do is find the horizontal component and the vertical component. But first, what we're told is to, well, I guess we'll find the ordered pair in component form first. Okay, so for the ordered pair, all we have to do is subtract. So notice 2 from, 2 from. So we'll put these little pointy parentheses, and it goes 2, if we look at our x values, it goes to -2, and it comes from 7. And in terms of the height, it goes to -1 from -3. So be careful with those signs because, again, you know, when we have minus and negative, we just want to make sure we turn them into plus or positive. And subtracting this, we get negative 9, 2. I want you to look at this because I want you to think about what this means. This actually tells us that we go from a starting point here, we go 9 units to the left because of that negative. That's why that's important, and the order of the x's and the y's would be important. So we start here and we go 9 units to the left, and then we go 2 units up. And that is where our vector starts and gets us to where the vector ends with a terminal point. Okay? So this is going to be helpful because we can now find the magnitude. I'm going to put negative 9 here for direction, and I'm going to put 2 here for the direction. We can find the magnitude of our vector. And all we have to do is we say, well, it's going to be absolute value. Okay, absolute value of CD equals the square root of, well, we would actually put in negative 2 minus 7 squared plus negative 1 minus negative 3 squared, which is exactly what we did over here. So to be honest, if you want to just jump to the chase, we could use what we just learned or what we just figured out and have negative 9 squared plus 2 squared. And again, we're looking at just another form, Pythagorean theorem. You know this. So we get negative 9 squared, which is 81, plus 2 squared, which is 4. So we get a magnitude of 81 plus 4, which gives us the square root of 85, and we can approximate that at 9.2. And that should make sense, okay? So again, we've made a right triangle, we've gone 9 units to the left, 2 units up, and we want to know, well, how long was the vector? About 9.2 units. So what I'd like you to do right now is I'd like for you to try and write the ordered pair that represents the vector. Now again, remember, from 4, 9 to negative 5, 3. Okay, so you're going to write the ordered pair using component form, and then you're going to find the magnitude. So pause this video, go ahead and do it, and then check back and see if you got the right answer. Okay, so how did you do? I wanted to point out that if you look at your vector, okay, it's starting here and it's going in this direction. So you should know when you're doing your order here, you're going left a certain number of units, so that would be negative. That's where we got our negative 9, and down a certain number of units, which is that 6. You might have made your triangle this way, and guess what? It's the same thing because you're still going left 9 and down 6 units. Okay? So, something that I didn't ask you to do on this particular problem was find theta, find the angle. What rotation is this at, or what direction is it going in? So what we really have to do here is we have to think of this as our own little coordinate plane right here, with this being the origin. And what we have to try to find is, if this is 0 right here, how many degrees is this? So what we'll do is we're going to think about using or calculating this angle because we're going down 6 and we're going to the left 9. So here is theta. So what I said earlier when we jump to the chase, we have to write the whole thing out, is we can say theta equals inverse tan of the opposite over the adjacent. So the opposite is 6, and the adjacent is 9, and those are both negative. Okay, so in our calculators, we can do inverse tan of -6 over -9, or just 6 over 9. And what we get is 33.7 degrees. Well, what we have to remember is that this angle is 33.7 degrees. So we must add 180 degrees to our answer so that we actually get the correct answer. So again, this gave us 33.7. But that would be in the positive. That would be in the first quadrant if we just had a little rotation like this and our vector was going this way. So what we're just going to do is we're going to add 180 degrees to that, giving us a 213.7 degree angle. Okay, so we put theta in here. We do inverse tan of the opposite over the adjacent, and then we make an adjustment if it's not going in the right direction, which it clearly wasn't. The 30-degree angle would have brought us, like I said, to the first quadrant, and we needed to be down here in the third quadrant. Okay? All right, last thing, last little bit, is that we can do all kinds of operations with vectors. Okay, and what's nice is we can do our operations using component form. So, for example, we can add these two vectors to each other. And all we're going to do is 1 plus 0, which is 1, -4 plus 4, I'm sorry, -4 plus 8, which is 4. Okay, and that is the sum of those two vectors in component form. We can also subtract. So we have u minus v. So we have 1 minus 0, which is 1, and -4 minus 8, which is -12. Okay? We can scale a vector. In this case, we're scaling it by 1/2. So half of vector v, you just take half of each component. So half of 0 is 0, half of 8 is 4. Okay? And letter D is a little mixture of all of this. So we're going to take 2 times u. Okay, so 2 times this vector gives us 2 -8 plus, and it says 3 times vector v, so 3 times this, so 3 times 0 is 0, 3 times 8 is 24, and now we're going to add them, and what we get is 2 plus 0 is 2, -8 plus 24 is 16. Notice we used our order of operations there, so vectors work similar to anything else. We have to follow the right order of operations. Okay? If you have any questions, go back, review this video. Hopefully this was pretty clear. Okay? Have a great night, everybody.